Hello, this is Jenna Nichols. Today we're going to talk about structure 2.4.4 and 2.4.5 from IB Chemistry. And this is all about polymers. Now, polymers are very large molecules, macromolecules made from repeating units of monomers. And then we're going to look at addition polymers, which form by the breaking of a double bond. So let's review a structural and condensed structural formulas really quick because we're going to need that for this section. Structural formulas show all of the bonds. So if I have something like butane, 4 carbons, each carbon can form 4 bonds total. And so since it's a hydrocarbon, all of those additional bonds for carbon will be filled in with hydrogens. So that is the full structural formula. The condensed structural formula puts all of the hydrogens next to the carbon that it's attached to. So this carbon has 3 hydrogens, the next carbon has 2 hydrogens, the next carbon has 2 hydrogens, and the last carbon has 3 hydrogens. That's the condensed structural formula. And then anytime you see where there's something that repeats, you can actually condense it even further. So CH3, CH2 twice, and then CH3 again. Both of these are called condensed structural, that you might see either one. And then the molecular formula just shows the number of each type of atom. So this is C4H10. That's the molecular. You're going to see that less in this section because we want to know about the structure of what's going on. Another thing I want to point out and just review really quick are some of the prefixes for organic molecules. Remember that meth means 1, eth means 2, prop means 3, but means 4, pent means 5, and hex means 6. So when we're talking about the numbers of carbons, this structure has 4 carbons, so it's a butane. And then with the ends in ane, that's only single bonds. If it ends in ene, there's at least 1 double bond. If it ends in ine, there's at least 1 triple bond. And so you're going to see a lot of both of these here, single and double, for this section. So as I said before, polymers are macromolecules, so very large molecules that have repeating units of monomers. Remember that prefix mono means 1, so a monomer is a single unit, whereas a polymer has multi things, depending on what you're adding together. Like you could add a bunch of amino acids. If they're separate to begin with, when you put them together, it's going to make an amino acid chain. So these would be monomers, and this would be the polymer. Basically, every biological molecule is going to be a polymer. So proteins, DNA, RNA, fatty acids, depending on the structure. And then carbohydrates, a lot of them are also polymers. So you have monosaccharides, or single sugars, or disaccharides would be double sugars, and then you could have a polysaccharide with many sugars hooked together. So all of these different polymers just consist of multiple small units hooked together. Okay, so let's talk a little bit more about plastics. So pretty much when we're talking about polymers that are not biomolecules, they're going to be plastics. And plastics are very, very stable. Typically, you're going to have monomer units. I'm going to use just a circle. And they're going to be attached to each other by covalent bonds. And these covalent bonds are difficult to break apart. A lot of microbes are not able to get in there and break apart those very stable covalent bonds. So that is a good thing and a bad thing. They're very, very stable, good shelf life, right? They're going to be more food safe because they're resistant to those microbes. But they're also propose a problem for recycling because these plastic products and even microplastic fragments are going to just persist in the environment for a very, very long time. So there's pros and cons for these plastic products. Another thing you should know, in general, the longer the chain for a plastic, or for any polymer really, they're going to have increased strength. It will have a higher melting point. And that higher melting point is usually because it has stronger London dispersion forces because of the long chain. And some of them are going to have a lot more branches, depending on the type. Not all of them, but some of them will have more branches, which gives it additional strength on top of just the increased London dispersion forces. So those are some general properties of plastics, and let's look at some more specific things. Two types of plastics are thermoplastics and then thermosets. Thermoplastics are typically made from alkenes. So remember, enes are double bonds, so they're typically going to be those addition polymers. And the good thing about thermoplastics is that they can be remolded whenever they're heated. So these are the ones that can typically be recycled well because you can heat it up, reshape it, change it, which is nice. Whereas when you have thermosets, there are different types of thermosets, but they basically, once you heat them for the first time and mold them the first time, they set and then they cannot be reformed. So they are irreversibly hardened. And some examples of that are things like Bakelite, polyurethane, vulcanized rubber is a good example of that. Not all rubbers, but vulcanized rubber is like when it's been hardened, are thermosets. Now, some plastics are going to be more elastic, and some of them are going to be more plastic, or like plasticity. So elasticity is when you can essentially stretch, and it's going to bounce back into its original form. Compared to plasticity is a property where when you stretch it, it's going to stay in the new shape. So rubber, regular rubber, is going to typically be an elastic substance, an elastomer, we call it. But other things will be more, have more plasticity. So it just depends on the particular polymer that you're dealing with. Now let's get into addition polymers. And these are polymers that form when a double bond is broken. So the simplest example is when you have ethene. Ethene. Remember, eth means two carbons. The ene means there's a double bond between them. And carbon always has 4 bonds. So you'll have 2 hydrogens on each carbon there. So that's a molecule of ethene. If I have 2 molecules of ethene, like this, what can happen is that those double bonds can break. So both double bonds can break, and then I can form a new bond between those 2 carbons. And the carbons on the ends are free to do the same thing with additional units of ethene. So this one's called polyethene, the actual polymer. Polyethene, because you're putting multiple units of ethene together. This is probably the simplest addition polymer you can form. The generic way that we would write this then is using parentheses or brackets. Some people use brackets. So you'll write it like this, CH2CH2. And so you can see that, let me redraw it this way so you can see it. The ethene original changes into this polyethene polymer. And so this version that I drew up here has 2 units of ethene, And depending on how many are stuck together, that's going to tell us how big that polymer is going to be. We usually use an N to represent the N number of the monomer particles stuck together. So let's look at some more examples of addition polymers. If you start with this compound here, which is chloroethene, it's called a chloroethene because it has a chlorine, 2 carbons, and a double bond. And then you have 2 of those units. When you break the double bond, you're going to form this repeating structure here. And so we're going to draw that using the polymer notation, CH2, and we'll do condensed, CHCl, repeating an N number of times, N number of monomers go into that. I'm going to redraw this back as the individual units. You can see it. So the 2 units would come together, and this is the repeating form. So we call this polychloroethene because it's a polymer of chloroethene molecules. Chlorine, eth is 2 carbons, ene is a double bond. But this ethene used to be called vinyl, like a vinyl group is a double bond group. So the old name for this, and it's kind of stuck around, is called polyvinyl chloride, or PVC. So when you see PVC, it's this compound here. Another example would be if I start with tetrafluoroethane. Tetra means 4, so tetrafluoro. And so if I'm going to just assume I have 2 of them together, and then the double bond breaks to form the addition polymer, it looks like this, CF2, CF2 repeating, right? And so this would be poly, tetra for 4, fluoro, ethene, so 4 fluorines, 2 carbons, and a double bond. When you break the double bond, form the polymer, it's polytetrafluoroethene. And the trade name for this is Teflon, which is the nonstick coating that you guys should be somewhat familiar with. Some polymers have benzene. Now, benzene is special because it has 6 carbons in a ring structure like this, and then it has alternating double bonds. And because those double bonds alternate, they can actually, the electrons that are in the double bond, they're pi electrons, they can actually delocalize and move throughout the whole ring, which makes benzene super stable. So these additional electrons, the 6 extra electrons, can move throughout the whole ring. So what we do is we'll draw this very often like this with a hexagon with a circle. And so this whole big ring structure is the same thing as drawing this. It's just that chemists are lazy and we draw the shorthand. So let's say, for example, for our polymer, I have that benzene ring, and attached to it I have an ethene group. Okay. You can still form a polymer of that. It would just break the double bond here and attach to another group. And so when that happens, you wind up with, I'll draw 2 groups together so it's easy to see. Like this, attached to CH2, attached to another carbon, like this, CH2. So that would be 2 groups for this polymer, and etc. And this is actually the structure polystyrene, which you guys know as styrofoam. So just be aware that when you see the hexagon with a circle, that's benzene, and its full structural formula looks like this with the alternating double bonds. So let's look at some example questions. This example says draw the polymer formed from propene using the N notation. So propene, prop means 3, ene is a double bond. So you're going to see like this, 3 carbons, 1 double bond. and then you fill in hydrogens because carbon has to have 4 bonds total. This carbon needs 2 more hydrogens. This carbon only needs 1 more hydrogen. This carbon needs 3 more, so that every carbon has 4 bonds. Now the easiest way to figure this out is to isolate just the double bond. So I have my double bond, and everything else should go up or down. It's much easier that way. So the CH3 from here goes up. I have the CH, and this I'm going to just write it like this. So it's a condensed formula. And then to help you see how the structure works, you can draw a second one with a double bond broken. And when this double bond breaks, you're going to form an attachment there, like that. So let's draw it now, actually using the polymer notation. So what happens, you'll look like this: CH2, single CH, CH3, like this, N notation. And that is probably the easiest way to figure out the monomer. Figuring out the polymer notation from the monomer. Okay, one more example. Draw a polymer made from 3 molecules of but-1-ene. So but means 4 carbons. And then this 1 in the middle tells us where the double bond is. So for butene, you could have the double bond in the first position or in the second position. The third position is the same thing as saying it's in the first position, just flipped around. So in this case, since it's but-1-ene, it's going to have the double bond in that first position. And then we fill in our hydrogens. 2 hydrogens, 1 hydrogen, 2 hydrogens, 3 hydrogens. Oops. Like that. And then you can isolate the double bond, like this. And we have CH2, CH3, like that. I'm sorry, it kind of got squished up here. But this way it makes it much easier to draw your polymer. So you're going to have that repeated 3 times. So I'm going to draw my continuation here. Single bond CH, CH2, CH3. So that's 1 unit. Then you do it again. H2C, CH, CH2, CH3, H2C, CH, CH2, CH3, and then it continues that way. So this would have 1, 2, 3 units of but-1-ene. Now you can, and I'm just drawing this so you can see the double bond between the carbons really well. A lot of times you'll see people do CH2 like this instead. It's the same thing. Same idea here, CH2, CH2. I just wanted to really clearly illustrate the double bond between the 2 carbons for you guys. So the linking questions here, and links to structure 3.2, structural features of some plastics that can make them biodegradable. Remember we talked about how a lot of plastics are not biodegradable, which makes them a really big problem for the environment. There have been a lot of developments in newer plastics that are biodegradable, and some of those features include like having an increased surface area so that bacteria can come in and break those bonds a little bit better. Shorter chains make them easier to break down as well. They could also have functional groups that make them more like able to be attacked by microbes and broken down by microbes. So sometimes you'll see polymers that have carbohydrates or sugars that bacteria can use as an energy source. And so it really depends on the specific plastic, but there have definitely been advancements in the structures of different plastics to help make them biodegradable versus not biodegradable and an environmental hazard. And then it also links for 3.2 functional groups and molecules that can enable them to act as monomers for addition reactions. You're definitely looking for that double bond. So we said it's an alkene functional group. That alkene is going to be able to be split to form that addition polymer. And then also we have linking to 2.1, atom economy. Why is the atom economy 100% for an addition polymerization reaction? So if you haven't covered this topic yet, atom economy is the mass of the desired product over the total mass of all of the reactants times 100 because it's a percent. So in addition polymerization, you are taking two alkenes or more, but you're basically putting them all together. And there's no other side products, nothing else is formed or released. So the mass of our reactants is equal to the mass of the desired product. So that way you'll have a 100% atom economy for addition polymerization.